Hello everyone, my name is Shri Yarlagada and I am your OChem Weekly Review tutor. So welcome back. We had a week-long break due to the winter storm, and it looks like your exam has been moved to March 3rd, which is a week from now. Today is Monday, February 22nd, I believe. Yeah, so we have about roughly around 10 days. So we have this week and then next week before your final or your first exam. So this week I am going to go over some practice problems posted by your professor. At least this is from Professor Tran, I believe, or On. I think it's Professor On's e-learning. This document is posted on his e-learning as well as the key, and of course you can practice it yourself, but I'm going to walk you through this entire packet full of practice problems, which covers both all three IR, Mass Spec, and NMR. So I thought it was a good resource to walk you guys through my thought process when solving these problems. All right, so let's get started. So the first thing to note here is the formula, which is C3H5BrO2. And then if you guys have seen my NMR video, you should know that the first thing I always recommend is to find your degrees of unsaturation. So we're going to do that. So we're going to, if I can figure this out, there we go. So we have C3H5BrO2, okay? So if you guys remember the formula, it's 2 times carbon, so 2 times 3, plus halogens and hydrogens you have to subtract. So there's 5 hydrogens, and then 1 halogen. So altogether, and of course divided by 2. Okay, let me double check my math. So 6 plus 1 plus, so 0 over 2. Okay, so that we basically have 0 degrees of unsaturation. So that means there are no double bonds, which means there are no carbonyls. But we might have done the math wrong, so we will come back to that. But I believe I did this right, the degrees of unsaturation formula. All right, so we have 0 degrees of unsaturation, and looking at this, it does look like a carboxylic acid. And then looking at the IR, rather, let me use the pointer. So if you notice, this mountain peak kind of resembles a carboxylic acid. And then this peak right here, 1717, I want to assume it's some type of ketone. But we could be wrong because there's only 2 oxygens. And if we say this is a carboxylic acid, this cannot be a ketone anymore because carboxylic acid uses all of our oxygens. Okay, so we're just going to keep those in mind for now. And it tells us there's 2 peaks right here around 2500. That doesn't really tell us anything. So let's go to the mass spec and see if we can figure something out. We also want to note bromine, and note that there's only 3 carbons. So it's a very small structure. And then 152 is our molecular weight. So taking a look at our mass spec, 152 and then 73 is our most abundant fragment. Just to refresh, the most abundant fragment means the most stable fragment you get whenever you cleaved it. So just to do a quick math right here, 152 minus 73. So I believe that is, one sec. So it's 79, okay? And if you guys remember from the mass spec weekly review, I told you to remember certain patterns and certain numerical values to help you solve problems quicker. So methyl is 15, ethyl is 29. So we just add 14 to our number. So 29 next is 43, 57, and then after 57, 14 is 71, and then 85. So it looks like that does not help us. Let me make this bigger. Okay. And the reason why I did 152 minus 73 is to get some type of fragment to see if we can, when we put it together, so we can double check it. Of course, there's other factors here as well. So I personally did not find anything useful. So I'm still a little bit confused, and this might be your thought process too. So let's go to the mass spec and see if we can pick anything out. Okay, so we have 2 hydrogens here, 2 hydrogens here, and then 1 hydrogen's very broad exchanges, which is around, I'm assuming it's this. This graph is not the most clear H&MR graph. So I see a peak right here, but it tells me some information right here. I'm going to assume it's, okay. So 2H, 2H, it's around 3 to 4. So it could be an ether or an ester. Those are the ranges. Ether is 3 to 4, and then ester is 3.5 to 4.5. Okay, so it looks like it's closer to ethers, and that would make sense since we have 2 oxygens, bromine, and then some carbons. And then I have 2 hydrogens, so I have 2 CH2 groups, okay? So that's what this means. And then 1 hydrogen alone means there's a single hydrogen not neighboring anything. So 2 CH2, CH2, okay. So let's try to take a guess at this point. It also gives you the CNMR. I'm not a big fan of the CNMR. I think it's better to use HMR, but we do have a peak around 180 and these 2 peaks. So I'm assuming this 1H bond is also somewhere here. And then let's take a look back. So 1717. Okay. So 3 carbons, 5 hydrogens, bromine, and oxygen. So yeah, let's take a guess at what this looks like. I'm gonna. So yeah, the spectroscopy is you have to use patterns of these tools that they give you, but sometimes it's also not a bad idea to just guess. And what I mean by guess, I mean by trial and error, really. Oops, didn't mean to do that. Okay, looks like there's no undo button on this. Okay. So again, like I said, so 3 carbons and an oxygen. So here are some possibilities. Okay, so looking at this, this could be a possibility. So because we have 3 carbons here, 2 oxygens, bromine, and then 5 hydrogens. We have 3 right here, 2 right here. So that could work. But of course, we have to see if, so we drew something related to our formula, but we have to see if that adds up to our graphs. Of course, our mass spec is going to be, our molecular weight is going to be the same as long as we have all of these atoms. So just based on the NMR that we saw before, this does not match because we're supposed to have 2 CH2s and not, so we're not supposed to have any methyl groups. So let's keep that in mind while we attempt the next one. And this time we did a ester with a 1 degree of saturation. So that's the part I accidentally erased, which is the degree of unsaturation formula, and which we got 0. So we should not see any double bonds, no rings, any of that sort. So we're gonna do it again. Instead of ester, we're gonna try 2 ethers this time. And then probably one of them is an alcohol based on our single hydrogen. Looks like that won't work either. Actually, wait, that is 5, but we're missing a carbon. So I see 1, 2, oxygens fit, hydrogens fit, bromine fits, degrees of unsaturation fits, but the NMR doesn't quite fit. Or sorry, the NMR does fit because we have 2 CH2s, 1 alcohol hydrogen, but we don't have enough carbons. We only have 1, 2. Okay. So give me 1 second. Let me take a quick look at what the answer key says, because this is also tripping me up. So, and yeah, I'm glad we're doing this because you get to see that, you know, even I have difficulty with stuff like this and clearly need some practice. Okay, all right, I see. All right, so let's get back to sharing the screen. All right, so what happened is, remember how I said this is a carboxylic acid like pattern, and then we also have the 1717, right? Now usually IR signals on this tells you that it's some type of carbonyl. Carbonyl and carboxylic acid means it kind of matches carboxylic acid. These two go together. So that means we did our degrees of unsaturation incorrectly. Okay. And I'm not sure why. Maybe I'm supposed to add halogens. So let's see. So 6 is what we get, and then we subtract 5 because so we're left with 1, and then maybe we add 1. But from what I remember, we subtract hydrogens and halogens and we add nitrogens. Or maybe it's the other way around where we also subtract nitrogens. Well, in either way, we get 2 divided by 2, which gives us 1 degree of saturation. So I'm going to assume that we do count bromine, which is a halogen, in our problem, in our degree of unsaturation formula. And notice I'm not doing anything with oxygen because that is not included in the formula at all. It's only carbons, hydrogens, nitrogens, and bromine, or rather halogens. So 1 degree of saturation as well as the IR tells me that there has to be a carboxylic acid. And with that information, this completely changes our guesses. So I'm going to delete all that because those answers were wrong information. So what we did get right is the alcohol part. And then, of course, we know there has to be 2 oxygens. That fits our formula. Oh, sorry. Let me get rid of that. Oh, okay. Sorry, I'm trying to get used to this PDF editor so I can draw on the practice problems for you guys, but I'm having some slight difficulties. So 3 carbons, so we already have 1 carbon, so we just have to extend it. And then lastly, we have the bromine at the very end. Okay, there we go. All right, so let's double check our work. We have 1, 2, 3 carbons, 2, 2, 1, 5 hydrogens, 2 oxygens, 1 bromine, so that works. Our IR, we have a carboxylic acid here, we have a carbonyl peak here, all of that fits for here. Molecular weight, it should fit as long as we have the right formula. And normally you don't need to double check each individual fragment for mass spec. If your formula fits, your IR fits, and NMR also fits, that usually means you got the right answer. Of course, there are circumstances where you have to maybe also use mass spec, but for this instance, we don't really need to. So I have 2 CH2s, which are these 2 right here, and then I have 1 hydrogen, which is shown right here, and it looks like it's actually pointing all the way here, and this is probably just an error or just like a misdirection. So stuff like that can throw you off. As you saw with me, I was thrown off. But it looks like it's somewhere in the 11 to 12 range, which is where carboxylic acid should be. But maybe this is not a mistake. Maybe this is the peak of the OH. But even that, I'm not really sure if that fits. But yeah, so there we have it. That's our first answer. Granted, it did take longer than it usually does for me, but there we go. All right, so hopefully all of that made sense to you, because we're gonna attempt the second one, and hopefully it'll be much smoother. All right, so this time we have C8H14, 4 oxygens. So again, we're gonna start out with our formula. So 8 times 2 is 16. 16 times 14 equals 2. I see no nitrogens, I see no halogens, so I'm going to leave it as that. Divided by 2 equals 1. So I know for sure I have 1 type of double bond or ring or any 1 degree of unsaturation. And looking at our IR peak, it's the 1749. So that means that there has to be some type of carbonyl. And then I also see a peak at around 3000, 2986. And then of course these we can just ignore because these are the fingerprint region. Okay, and our mass spec, our molecular weight is 174. Again, we don't need to mess with mass spec unless we need to. That's personally how I feel. Of course, there are many different ways on solving a spectroscopy problem, a combination of spectroscopy problem, rather. So I'm going to go straight to the NMR. And it looks like we get some multiplicity also given to us, and looks like they're all under around 4. So we don't have to worry about benzene rings or carboxylic acids or aldehydes. And well, we shouldn't have any of those to begin with, or at least not a benzene ring, because we only have 1 degree of unsaturation. To know if you have a benzene ring or not, your degree of unsaturation should be 4 or higher, because 3 double bonds in the benzene ring is 3, and then the ring itself is another 1, giving you a total of 4 degrees of unsaturation. And then you should also see a peak at around 1600. All right, so going back, so I see 6H, which means it's 2 methyl groups that have some type of symmetry, 3H, 1H, and 4H. Again, 4H means there are 2 CH2s that have some type of symmetry. And normally when I see 2 symmetries going on, that means the structure is very symmetrical. And of course, 1H and 3H we also have to keep in mind. And then, yeah, again, like I said, I don't see any significant peaks on the IR other than the main one, the carbonyl one, 1749. And then, of course, we have 4 oxygens and lots of carbons. Usually lots of carbons tells me that there's some type of benzene ring, but here, as we already found out and determined, there's no benzene ring. So we're just going to have to do trial and error again. And 4 oxygens means, 2 esters, 4 ethers, 4 alcohols, 4 ketones, any combination like that. But as we already found out, we only have 1 degree of unsaturation. So it can't be 2 esters. It could be 1 ester, 2 ethers, 4 ethers. It could be 1 ketone, 2 ethers, many combinations. So I'm gonna rewrite the formula. So C8H15O2O4, I believe. Let me double check. C8H15H14. Okay. Oh, okay. So I'm going to attempt the 4 ethers direction because I've noticed a lot of symmetry. Actually, because of this 1H, yeah, okay, let's just try a combination of things. Let me move this. Oh. Let's try to move this. Okay, let's move that to the corner so we have more space. Okay, and then let's try drawing a couple guesses. So we know we have methyl groups, so I'm not going to shy away from that. So I'm just going to draw 4, but we have 8 carbons, so I have to make sure I keep that in mind. So, and then we have two symmetries. So, okay, 1, 2. It's not letting me connect. Okay. 3, 4, 5, 6. And then I'm going to place an oxygen right here. Place an oxygen here. Oh, 7. I can't erase just that one. Okay, so that does not work. So I'm going to have to delete that. Let's see. Did I have him do my math wrong again? Maybe 4, 6, 3. Okay, it's saying there are 2 degrees of unsaturation, so maybe they're not dividing by 2 for some reason at the end. Let me double check with the first question. So 6 minus 5, which is 1, minus 1. Well, that doesn't make sense. Okay. So it looks like it is 2 degrees of unsaturation, and so that opens up to lots of other options. So we can actually do the 2 esters possibility now. So I'm actually going to opt into doing that, and then keeping in mind symmetry as well. Okay. So we have an ester right here, and because we have 2 esters and there you know for sure there's symmetry based on the 6 and 4. That means you have to make one side equal to the other side. And I'll explain my structure once I'm done drawing and how I got it. All right, so first off, we have 4 oxygens, and then let's count our carbons. 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, looks like I have 1 extra methyl groups on each side, so get rid of that. Okay. I have to redraw that side. Okay. So again, 4 oxygens, 1, 2, 3, 4, 5, 6, 7, and then 8 with this extra methyl here. So carbons fit, hydrogens should fit, but we can double check. 3, 5, 6, 9, 11, 14. Okay, so that fits. So the formula fits. The degrees of unsaturation somehow fits. I'm not quite sure how. Because I got 1 degree of unsaturation, or yeah, so I got 2 over 2, which should be 1, yeah. Okay, so let's double check. So 6H means 2 methyl groups that have some type of symmetry. Those are this methyl group here as well as this. If you haven't noticed, there's a line of symmetry going down the middle. Oh. Like that. And then the single methyl group we see right here is the one in the middle. Sorry about that. And then the single hydrogen is the one in the middle as well. And then 4 hydrogens is the 2 CH2s. And because they're symmetrical, we have to count that as 4. Same with the 3 and 3 hydrogens. Because they're symmetrical, we have to count that as 6. Okay. Hopefully this makes sense with this structure. And it should also make sense with the mass spec when we have to look at these fragments. 174, 146. Yeah, that should make sense. And then the IR 1749, that should be closer to ester than aldehyde or ketone. And then these are just CH bonds. So really the most valuable information is the H-NMR graph as well as the formula. Okay. All right. So moving on. So C9H12. So this makes it very easy because you know there are no oxygens, so that means no ketones. Okay, yeah, I don't see any peaks right here, and we see lots of CH peaks right here, and that should make sense. All right, and it looks like we actually have a benzene ring. And the reason how I know this is because the benzene ring hydrogens are between 7 to 8. Okay, so already we can get some type of skeleton of the structure. So let me quickly remember. So C9H12. So I usually just use the H-NMR graph because it tells you the most information. Of course, IR can quickly tell you some functional groups, so that is helpful. But H-NMR will complete your structure, and of course it's whatever you're most comfortable with. That's why they give you all 3, because you kind of need some knowledge on all 3. So again, it's C9H12. Okay. So again, like I said, the hydrogens between 7 to 8 means that it's a benzene ring, and any formula that has above 6 carbons, you always have to have think about the possibility of a benzene ring. Okay, so I'm going to draw a benzene ring, and it says 5 hydrogens. That means we have 1 substituent at the top, or really anywhere. And then we have 5 hydrogens right here. So 1, 2, 3, 4, and again we don't have any oxygens. So because we already have a huge structure or a huge chunk of our structure already, we have to take account into what's left. So I have a triple bond, sorry, not a triple bond, a triplet, multiplet, 2 hydrogens, and a methyl group. Okay, and I use 6 carbons, so I'm missing only 3 carbons left. Okay, so I could add a chain of 3 carbons. We could try that, and that looks like that's the right answer. So let me just go ahead and write it in and see if it matches. So this triplet is neighboring 2 hydrogens, so that fits. This multiplet is 2 hydrogens, but it's neighboring 2 plus 3, so that's 5. That works. This 2H is neighboring 2, so yeah, this fits. So this one was very straightforward. There was not any functional groups outside of benzene ring. And notice there is a peak at 1602, so that signifies the benzene ring. And when you see a lot of peaks right here, that means there's just a lot of CH bonds. But the main thing was the 7 to 8 region. That basically gave you the rest of this. Okay. Let me just quickly double check just to make sure that's the right answer. Yep, that's it. All right, question 4. C7H13 bromine. I don't see any carbonyls, and that should be correct because there's no oxygens. Okay. Around 2800, 2900. Okay, that just means a lot of CH bonds and a bromine somewhere in the mix. Okay, so most of my peaks are 1 to 2s, 5H, 6H, and a double bond right here. Okay. So again, this tells me that there is some type of symmetry going on. But we can't just do a straight chain. This one has to be a ring also, but it's not a benzene ring. So I'll explain what I mean. So it should look like, so it's a cyclohexagon. So that's 6 carbons, and what was our molecular formula again? So 7 carbons and a bromine, and of course lots of hydrogens. Okay, so that means we're just missing 1 extra carbon and then a bromine. Okay, so I'll explain where everything is coming from and how I got that. So first, the molecular formula fits because we have 7 carbons, 1 bromine, and 13 hydrogens. Each of these have 2. So 2, 4, 6, 8, 10, 11, 13, 14. So formula fits. Mass spec didn't really give me anything. IR didn't really give me anything. So let's take a look at our graph, our H&MR graph, and see how that fits. I have 2 hydrogens that is a doublet, and that's going to be this one right here next to bromine. And the reason why it's a doublet is because there is a single hydrogen here. That's the only neighboring hydrogens. These ones are too far, and bromine doesn't count. So 1 plus 1 is a doublet, and the reason why this is the most downfield or to the left and deshielded is because it's right next to the bromine. Okay, the bromine tells me that it has a deshielding effect. Okay, and then 6 hydrogens, 5 hydrogens. Okay, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11 hydrogens are coming from this ring. 2 we already claimed with this. So let's see. So this is actually a HMR graph I haven't seen before, so I'm trying to make sense of it myself before I can explain to you guys. I'm assuming the one that is 5 hydrogens is including this single hydrogen and then 2 sets of hydrogens. Maybe these 2? Not really sure actually. But the good thing about this semester, or even any semester, you don't really have to make sense or explain your H&R graph. At least I don't think so. Especially with multiple choice, you definitely don't have to do it. But yeah, that should fit this. Maybe one of the professors can explain where each of the signals are coming from. All right, let's move on. Number 5, C5H8O. Okay. All right, I don't see anything important from this IR. Mass spec isn't really needed. Okay. 4H, again, if you see 4, 6, or 9, there's some type of symmetry, or 8, of course. 2H, 1H, 1H. So these 1Hs are very helpful and interesting, as well as this 4H. So C5H8 oxygen. So one oxygen tells me there could be an ester, and I think there cannot be an ester because there's only one oxygen. Ester and carboxylic acids have to have 2 oxygens at the bare minimum. And 1H and 1 oxygen tells me that there is probably an alcohol, and one of the other H's is probably probably like an isopropyl or something. And that would kind of make sense because we have some type of symmetry also going on right here. And we have to keep in mind there is also, actually never mind, there's nothing else. Okay, so let's see. Again, I'm going to rewrite the formula. So C5H8, I believe, H8 oxygen. Okay, so it's a rather short, small structure. I'm sorry, maybe I should zoom in for all of these. Okay, so hopefully that is a little bit better. Sorry about that. So I'm going to start out with my oxygen. Now I'm not sure if I should put it at the very end, or maybe I should put it in the middle, because like I said, there's symmetry going on. But again, we just have to trial and error with it. They don't really give us multiplicity, so I'm going to assume these are all singlets. Or maybe I really shouldn't assume anything, because this one, all of these could possibly be doublets also. In fact, all of them look like they're doublets, because I see 2 peaks. Well, anyways. Actually, these 2 look like they're... Yeah, either they're all doublets or they're all singlets, but anyways. So let's just go ahead and do the basic one that we're thinking of, which is putting the alcohol at the very end. And if we so we have to have 5 carbons, so 1, and there are no methyl groups. That's the most important thing. So there's no methyl groups, then I'm thinking it might be in a ring, potentially. Yeah, because it has to, because otherwise you're not going to get... There's no methyl groups, that means it can't be a chain. So it has to be a ring, and we didn't do degrees of unsaturation because it's not really matching up with the formula I have, but we can quickly do it. C5 is 10. We have to multiply... Oh, I think I'm forgetting to add 2. So the formula is... so 2 times carbon plus 2, and then subtract hydrogens, subtract halogens, and then add nitrogens. Okay, sorry. I'll double check with the other structure, the other columns, but yeah, so it's 2C plus 2 plus N minus H minus X. and all divided by 2. Let's see if that formula fits again with this. So that's right here. Okay. So 10 plus 2 plus 2 equals 12. And then I don't have nitrogens, I don't have halogens, so minus 8 gives me 4. Divided by 2 gives me 2. So there's 2 degrees of unsaturation. One of them which has to be the ring, and the other one is potentially just a regular old double bond. And that's probably what this is, because it looks like these are actually connected. And it's not a result of symmetry. And I'm not really enjoying these problems because they are very tougher than what I'm used to. So let's redraw these. So we're gonna have oxygen has to be somewhere in the ring, and then it has to be 5 carbons. So it's a cyclohexagon with oxygen as one of the parts. Okay. So everything works except we only have 8 hydrogens, and if you count, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have 2 extra hydrogens, and the best way we can do that is to add a double bond right here. Okay, now that fits our formula, that fits our degrees of unsaturation, and that also fits our graph, because like I said, these 4 H's, they look like they're next to each other in some fashion. But even if we ignore this, let's make sense of the rest of the graph. So we have 1H, 1H, which, you know, it could be these two right here, 1H, 1H. And then we have 2H. So the rest of these are all 2H's, but 2 of them are similar and 2 of them, or 1 of them, is different. Again, it's really hard to tell which one's which because they're not equal distance to anything, and I don't see a world where 4 H's can come here. So maybe I'm thinking maybe this double bond is not in the right place. But the only, because if you put right there, because yeah, so let's say we move the double bond over here, that's going to be the exact same, right? So the only other option is to put the double bond right here. And that would make this completely symmetrical, and there would be 4H, 4H instead of 4H, 2H, or does that make sense? If we put it here, okay, never mind. It won't be completely symmetrical. Okay, but let's see if that fits. So if we put it here, yeah, I think everything makes sense except this 4H, and I don't even think it's technically combined. I think it's just 2 separate H's. Maybe it's 2H, 2H, because that would make sense if it's these 2 and then this one is, or sorry, these 2 and then this one is the one closest to oxygen because it's electronegative, and it's de-shielding more to the left. Yeah, these are definitely good questions and good practice. Hopefully the real thing is much more straightforward than the ones here, because I will admit these are slightly tougher, and I'm not getting much useful information out of any of the Spec or IR in any of these graphs. But yeah, let's move on to number 6, I believe. Okay, yeah. So again, no oxygens, no bromine, so C6H10. So one thing we did learn is we figured out the right formula. I just forgot the +2. That didn't really, that part, because it was missing completely, you know, threw me off. I don't see any carbonyls, and again, I don't know what I'm looking for because there's no oxygen, so I can ignore that. So C6H10, so let's just go to our H&R graph. And I just want to remind you guys that this is a personal preference of me going straight to the H&R graph. If you want to dive into the IR or the mass spec, feel free to if you're comfortable with it. NMR is what I'm comfortable with. So I think it was C6H10. Okay. C6. So yeah, let's just do the formula. So 12 plus 2, 14. 14 minus 10 equals 4. So 4 divided by 2 equals 2. So we actually have 2 degrees of unsaturation. So we could have 2 double bonds, we could have a ring or 2 rings, or 1 double bond, 1 ring. There's no carbonyls because no oxygens. 4H, 4H, 2H. Okay, so some type of symmetry. And they're all CH2s. And this one is very high. So if you notice, even from the other one, right here. So these 2 hydrogens, they're they're like close to 5 to 6, right? That 5 to 6 range is actually your double bond hydrogens range. So because we see similar patterns here, 5 to 6, I'm going to assume there's a double bond again. And because there's a lot of symmetry going on, I'm going to assume, and we have 2 degrees of unsaturation, so I'm going to assume there's another ring. So let's draw a cyclohexagon with a double bond inside of it. So just a single double bond would fit our formula as well as our degrees of unsaturation. And then our 2H fits these right here, so 1H, 1H. And the reason why this time it's paired together instead of separately as our previous problem is because there's a line of symmetry down the middle this time. I know that doesn't look like it's in the middle, but I promise it's in the middle because there's a carbon here, carbon there. So there's a line of symmetry down the middle, and then these 4 H's are just on the sides. So 1, 2, 3, 4, 1, 2, 3, 4. Okay, so that one was more straightforward because we did the previous one, so we got a little bit of help and practice, so we were able to recognize it quicker. And that's all it is. OCHEM is just, you're just recognizing patterns that you've done problems before. So when it comes to actually solving it, you can just remember your experience and practice and apply it. Don't see any carbonyls, don't see any OH, alcohol, carboxylic acid, nothing like that, and that makes sense because there's no oxygens. C10H7 bromine. Wow, okay. So this is very, so hold on, C10H, I already forgot, okay. H7, okay, I thought, so I didn't forget, I thought I just misread that, but okay, wow, it's actually H7. And all 7 hydrogens have the same signal between the 7 to 8, which is aromatic. But benzene rings only have 6 hydrogen or 6 carbons. But benzene rings are not the only aromatic compounds. We have other compounds that can be aromatic. And we also have the bromine that we have to watch out for. So if it's not benzene, that means it has to be some type of dual ring combination, right? And I don't need to, I mean, I'll do the degrees of unsaturation to double check or not, or to get more information. So C10, so 20 plus 2, 22. 22 minus 7 gives us 15, and then minus 1 because bromine, that's 14 divided by 2 equals 7, so 7 degrees of unsaturation. And they have to be aromatic, and I just said it cannot be one ring. It has to be 2 rings that are aromatic. And I realize I keep throwing the word aromatic around, but I also realize that you guys haven't learned what aromaticity means, or you won't yet until exam 2. But basically, a benzene ring is aromatic because of certain features, which you will learn in OCHEM, the second unit. And in the second unit, they have different structures outside of benzene ring that also fit the same characteristics that make it aromatic as well. So again, I'm not sure why this question is in this because you guys haven't gotten to it yet. So let me try to reduce this. Okay. So again, 7, 2 of them I'm using for the ring because I'm assuming it's 2 rings. And then the remaining 5 are probably just double bonds because I'm not supposed to see any carbonyls or anything. Alright, so here is what it's supposed to look like. And I'm not sure how you're supposed to get this without exam 2 knowledge. So that's one structure. So you have the ones here, here. I think I drew it wrong. Yes, I definitely did draw it wrong. Okay. So instead of 2 pentagons, it's supposed to be 2 hexagons. So, okay, yes, we can delete all of that. And then so 2 hexagons, which are 2 rings, not benzene rings, but 2 rings. And then in that, so one of them is going to look like a benzene ring, but the other one only has double bonds right here and here. And it cannot have a double bond here because that would be too many carbons for these 2. And then last but not least, we have bromine attached to one of the carbons. I'm not sure if it really matters where. I mean, it probably does due to the mass spec and the IR, but I just put it right there because that seems the least risky one. But yeah, the reason why this works and the reason why it's 7H because this whole structure is technically considered aromatic. And I don't want to go too in depth with that because it's outside the scope of this exam. So I'm going to move on, and then maybe you guys can come back to it once you have exam 2 knowledge, because Nmr does not go away. You have to use it for every exam and even the final exam, unless they change things this semester. Yeah. All right. So looks like, let's see how many problems we have. 1, 8, 9, 10. Okay, so we have 3 problems left, but it looks I'm actually going to stop right here because we're reaching the end point. But I hope you guys learned something through this walkthrough. I know it wasn't the most cleanest one, and I wasn't like knowing everything. Just like you guys, I had some trouble with this too, but hopefully you guys have similar thought process as me, and using the answer key and using your existing knowledge, hopefully you guys can put those together and make sense of what the answer should look like, and hopefully it should match the structure you get should match each of the graphs, especially the HMR graph, because just based on what I'm seeing, um, it says IR, NMR, mass spec problems, but really I'm not getting much useful information out of the other two. Maybe the last 3 problems have more information. But yeah, I'm going to end it here. I will see you guys next week. Next week, we will probably do a full-on exam review, unless there's more material in your lecture, which I don't think there should be, but we'll see. And yeah, if you guys have any questions, make sure to come to the live weekly review so you can ask questions while I'm doing this, so I can answer it right away. Of course, you're probably watching this on a recording right now. So if so, make sure to practice NMR problems in addition to problems that have all 3 spectroscopy. Again, keep in mind the format your professor is going, the cutoff point of where lecture is to not go over or under. And yeah, I'll see you guys next week, but make sure you guys study throughout this whole week instead of putting it off until next week. But yeah, glad to have everyone back. Hope everyone's warm and staying safe. But good luck on studying and all the rest of your assignments and exams in your other classes, as well as OChem. And good luck.